the University of Arizona Bio5 Institute, we bring together hundreds of multifaceted experts that include world-class bioscientists, engineers, physicians, and computational researchers. This team science approach is designed to ignite creative solutions to the many complex biological challenges facing our families and communities, and has resulted in disease prevention strategies, promising new therapies, innovative diagnostics and devices, and improved food sustainability.
Hello, and welcome to another episode of Science Talks, a conversation hosted by the University of Arizona's Bio5 Institute. My name is Lisa Romero.
And I'm Brittany Ullorn.
From smartwatches to pacemakers, technology is essential in helping us lead happy, healthier lives. Some of this tech, though, can be bulky and a little intimidating, so creating inconspicuous devices that carry a big impact is at the forefront of tomorrow's life-changing innovations. Today, we are happy to be joined by Dr. Philipp Gutruf, Assistant Professor of Biomedical Engineering and Bio5 member. Dr. Gutruf specializes in creating new kinds of wearable and implantable devices that seamlessly integrate with living systems to ultimately change the landscapes of health diagnostics and neuroscience. Dr. Gutruf, thank you for joining us today.
Hey, great to be here.
So Dr. Gutruf, your research combines innovations in soft materials, photonics, and electronics to create novel devices. So can you talk a little bit about how these types of advances are going to help us better understand how the brain works and how we can enable new treatments or cures for things like chronic pain, depression, epilepsy, things of that nature?
Yes, yeah. So let me start by taking a couple of steps back. So if you think about contemporary devices that integrate with the human body, like for example, this smartwatch that I'm having on my wrist, it's essentially a brick that's strapped to you, right? The same applies also to, for example, a pacemaker, right? It's this large, bulky stainless steel case that you get implanted. And then the electrodes, they attach to your heart. The same applies also to wearable devices, right? They get strapped to the body. So now one of the fundamental problems is that our body is soft, right? The mechanics are completely different. And the way that our body sends information is also very, very different to our most sophisticated devices, CMOS circuits, all kinds of microelectronics. So what we are trying to do in my lab is to change the way that bioelectronics, or in general devices that integrate with the body, that they feel and work to create a more intimate contact to the body. So that's kind of the baseline of most of our devices. So one of the reasons why, for example, a smartwatch is pretty bulky, why a pacemaker needs to be that big, or why brain interfaces, are pretty big cables and you need to penetrate your skull to get these devices in, is mainly because the way that we power our devices relies on batteries, and batteries are pretty big, right? That's not only a problem for biomedical devices, but for example, for cars and planes as well. So what we are doing is we're taking these platforms that we try to make as biology-like as possible, and we integrate them with means to power them remotely. So we use, for example, electromagnetic waves that cast power into devices, or wireless power transfer that keeps these devices going 24/7. So that's the kind of technological foundation for most of our devices in particular. So now we have in my group two streams of research. One is implantable systems. You talked a bit about the applications in the brain and in the central and peripheral nervous system. So for example, the spinal cord, the brain, and other nerves, as well as wearable devices that are non-invasive, that are on the body, but still are in a very different form factor and operational principle that you would usually expect from contemporary devices.
That's really exciting. taking a step back even further, because I just think it's fascinating. When did did your brain always comprehend that, this technology would continue advancing, and, we would be able to think about having these types of applications, much less applications that actually really do move the needle, on diagnostics and prevention and potential help in managing diseases and disease states. I mean, talk me through how sort of you came into thinking about doing this, and what your training did to sort of incorporate that, and then I think also how how you started off being committed to that, but technology changed so rapidly, and how you see that sort of continuing to be used in your professional path.
Yeah, I think in general, the ideas are not necessarily new, right? If you look into
Right.
science fiction, various kinds of books, I mean, that takes various form factors depending on the authors. But the idea or dream is always that you just go about your daily life and everything else happens, right? We can remotely tell how you're feeling, what your current status of health is, right? And make diagnostics well in advance. So I think that the general dream of just not being interrupted with your tasks, with what you're doing daily, and not have to worry about healthcare. I mean, it's pretty much a burden, right? And nobody likes to go to the doctor. Nobody, likes to get their annual checkups done, and waste all of this time, or not waste, but spend all of this time on health maintenance, right? The best thing would be if this would all happen automatically. Now, obviously, technology needs to catch up to this, and we need to find ways in order to interface with the body in a way that allows this seamless interaction. And so maybe a little bit about my background. So I come from Germany. Maybe you can see that from my name or hear it in my accent. That's where I grew up. So my undergraduate degree was in sensors, or sensor system technology. And I then proceeded to do a PhD in actually Australia. That was electronic materials. So that was kind of my introduction into making devices stretch and bend. So there I looked into, for example, oxide materials that allow us to make stretchable sensors, or photonic devices that can flex. So the emphasis there was always to kind of enable current technology to be more compliant, mechanically compliant, to be closer to human body mechanics. And then I proceeded to do a postdoc at the John Rogers Group in UIUC, and then later on at Northwestern University. And that group pretty much pioneered some of the soft electronic approaches. What I developed there is capabilities to interface with the brain, for example, or collect certain biomarkers from the skin. So that's my education, where I come from. And now in my group, we really try to emphasize these technologies and bring the unique experience in wireless electronics to this platform, to enable very seamless interfaces. May that be for the central peripheral nervous system, or also for wearable devices. The idea, the goal is, and we can partially do this already, that you go about your daily life and everything else happens. Yeah.
I would love to not go to the doctor anymore, to just get, just get the basics measured and to be able to predict that. I think that's what, people don't understand. They're still, giving that. They just have to go somewhere to do it.
Exactly. Yeah.
Go ahead, Brittany.
Thank you for taking us through your, education. It's really clear to see how all of these different bits and pieces, how they've kind of helped form what you're doing in your lab currently, and how you've kind of moved with the trends and that nature. And I know you mentioned a lot of different fields like photonics and optics and sensors and electronics, but we're also talking about the human body and the brain. So it's clear your work is very interdisciplinary, which is exactly at the heart of what we're all about at Bio5. So I'm also just curious, do you find yourself collaborating with people from other disciplines a lot to be able to bring in that expertise to help inform how you make your devices?
Of course, yeah. This is essential, right? I'm in biomedical engineering is my home department, so it is really important. Or the possibilities, especially here at the University of Arizona, really help us to do our research well, right? We're just a couple of steps away from the hospital. So just to give you one example why that's super important, we have this new device class we call osseous surface electronics. So these are thin electronic sheets of paper. You can think about this as it's literally as thick as a piece of paper. These devices, they allow us to capture a lot of information about bone health. And we can grow them onto the bone to form this permanent interface, power them wirelessly, and we extract the data also completely wirelessly. Now, the initial impulse came actually from a conversation just after I started, maybe 2-3 days or so after I started here at the University of Arizona a couple of years back, where folks from the med school had research projects where they laminated strain gauges onto the bone in order to understand bone health or bone regeneration, various kinds of mechanisms on a fundamental level. Now, they always would have loved to have this in a form factor that allows them to take these measurements all the time, because that can really inform how we can do therapeutics, for example. It really informs our basic understanding of how bone health how bone health works in general, right? There is no means of doing these measurements right now continuously, because if you have wires attached, you can imagine, right? There's a large infection risk, so you can do only momentary studies for a relatively short amount of time. So this is really where we can then come in and bring our expertise in soft electronics and wireless power transfer to then create devices that are, only that big, 2 post stamps or so, that you can then laminate onto the bone and get that data. So yeah, this wouldn't be possible if all of these people wouldn't be in very close proximity. We can make devices, walk directly over to the hospital and get them tested. So really, being able to interact with clinician scientists and also clinicians to get this direct input for the clinical need for these devices, and then be able to react quickly to current ongoing trends is really important. And that's what Bio5 certainly facilitates, and in general the University of Arizona.
I remember a few years back. When did you come to the U of A? I can't remember when you started.
It's maybe 3.5 years ago.
Yeah. I think it got close when you started. I remember sitting in a meeting, and you were not there, and it was related. It was some of our brain researchers, and they were doing some brainstorming about some potential content for a big grant they were putting in at the time. And I remember, I think you had just started, and one of them just all of a sudden was, wait, I know somebody that just started at the University of Arizona that's doing some work with songbirds that could potentially, play into this grant, and how it applies to ways that we can help, get data on brain and just integrate into this. And I mean, of course, at the time, I had no idea, what they were referring to, and they didn't even know a lot about it. But I think it's absolutely fascinating, and I think you've gone a little bit further with that project. So can you tell us a little bit about that? And
yes,
somebody that has, brain disease in my family very significantly, that novel ideas like that are pretty incredible. So I'd love to hear more about that.
Yes, yeah, this is also a project that kind of grew here at the University of Arizona, because we have researchers just across campus that work with these very rare animal models, so relatively not usually available, and those are songbirds. It's the only animal model that allows us to study how we acquire speech in small animal models, right? And how the brain kind of deals with learning and also vocalization of speech. As you can imagine, if you've seen songbirds, right, they may be this size, right? They're tiny. So typical instruments that we have currently to probe what's going on in the brain, they're bulky. They don't allow the birds to move around freely, and that is a big problem for songbirds, because they don't sing if they're not happy and if they're not, in their usual environment. But it's essential for them to practice their song. They learn it from their parents, and they use it then in order to find their mate, which we can use the cycle in order to understand how the brain works when it comes to speech. And so when I arrived here, some people knew about the work they have done beforehand, being able to create these tiny electronics devices that operate without any wires associated with it, that have no real mass associated with them as well. We figured out that we could actually make photonic interfaces to the brain that allow us to modulate certain neuronal groups that are important, or that they suspected are important for language formation. And so this project is actually published just fairly recently, maybe half a year back, where we could demonstrate for the first time to have these freely flying untethered animals where we can modulate the song. So we showed, for example, if you modulate certain neuron groups in the brain, you can shift the pitch of that song up or down depending on modulation. So that is a tool that's now available for the scientific community to really try to understand how the brain acquires language.
Wow, it's incredible that your research, I mean, it's clear your research has so many applications, and it touches so many different models as well. So it's neat to see that collaboration across the university takes you all the way from looking at thin devices for bones to looking at pitch and songbirds. It's just clear how wide your impact is. And I kind of want to touch on even more of your impact and switch gears a bit away from research. So I know you also routinely teach a couple of courses in like medical device design and biomedical engineering research. So I want to know if you could speak to us a bit about, your passion for educating future biomedical engineers, and, maybe tell us what are some of the biggest lessons that you like to pass on to your students.
Yes, yeah. This is actually quite a complex question, because I try to really diversify the way that I teach biomedical engineering to students. So there is the traditional course component, and what we could recently do is we had the possibility to build a completely new facility that allows us to teach students hands-on skills in biomedical device design. So this was enabled by some really generous donors, the Salters, that allowed us to build this particular center. It's in AME. When you walk past the courtyard, you'll definitely see it. So this allows us to, for example, do electronics, mechanics, chemistry, and biology, all hands-on, all in one building. So it's really engineering paradise for biomedical engineers. So that was, or that is one project of mine. I currently teach the BME 310, which is the biomedical device design course, and there we really emphasize not only designing, so we go over clinical need, for example, and what devices need to look like in order to really have impact, but we also build them physically. So these students come up with prototypes for devices that they create completely from scratch: electronics, mechanics, photonics. We have a competition at the end of the course. Last year's focus was prepare for the next pandemic. So they had to come up with, what's most likely going to happen again, and come up with devices that allow us to mitigate the devastating impact of these particular events. So they came up with really cool devices that manage, for example, stress of first responders, or that manage well-being of people that are isolated because of this. So that's really engaging, and also really cool to see the creativity of these fresh young minds. So that is one of the courses that I teach. But I also make sure that I have a lot of undergraduate students participating in our research. This is what motivated me. Maybe a quick background story to how I got started in science. I didn't set out to do a PhD, actually. This is something that I kind of walked into. I was able to, or I traveled a lot when I was younger, and I was always motivated to find kind of new opportunities and places to experience, new cultures to experience. And during my undergraduate research, there was this opening in Australia that allowed me to do research. And beforehand, I haven't actually done research. It was this opportunity that was a kind of a funded scholarship that allowed you to travel there, do research for a year, and use that as in Germany you have to write like a mini thesis for your bachelor's degree. And so I did that and really enjoyed this. I had this clean room basically available whenever I wanted to, and the supervisor were fairly hands-off, and they told me, okay, we would like to have the sensor and it should be stretchable. Find out a good way to do this. And so I really got interested in the process of science, and that really allowed me to, for the first time, to really accelerate my learning as well as my output by completely driving my day by myself and explore. So that's how I got started in science. Beforehand, that wasn't my intention. I didn't really tailor my academics towards continuing there. I probably thought that I wanted to go to industry, but this was really a turning point for me. So I want to open the same opportunities to undergraduate students here at the University of Arizona. So we have a lot of undergrads participating in research projects. At the moment, I think we're well over 10 or 15 undergraduate students in my lab at this point in time. And they all contribute to projects. We had actually a couple of students that really used this chance to accelerate their own career. For example, we had an astronaut scholarship recipient in my lab. That was on several high impact papers, and he really was able to build up quite a bit of knowledge in finite element simulation in order to simulate electromagnetics as well as mechanics for these type of devices that we build. There was also a student that now is the first, let me see if I got that right, the first Hispanic or Latina that got the Oxford scholarship, also Oxford Fellows, I think the name was. So I think she was for a couple of years in my group as well. So in general, I really enjoy these success stories by opening up the group, enabling them to do actual research, being able to get on papers, to really contribute to the work that we do. To kind of spark that curiosity in the next generation, like it happened for me. So
that's probably one of the best examples, and I will steal that for people I talk to in the future about. We have a lot of visitors and a lot of people we talk to about Bio5 and the nature of what we do and what our incredible researchers do, but something that Dr. Barton, the director of Bio5, believes very strongly in, and we all articulate as often as possible, is this, many people, I think, see a research mission and an education mission at a university as sort of parallel but separate tracks, right? Like, I mean, they're a lot of people assume they're for two different endpoints. And, at Bio5, what our goal is to blend those two things. Instead of having them run parallel to each other as goals, we merge that into a goal. And I think you described that beautifully, in terms of the impact it can make in both areas, right? It is better for educating our students to have hands-on opportunities to sink or swim, like you got, and now you're giving back. One of my favorite sayings that isn't exactly probably politically correct, but is fake it till you make it. You learn and then right? But you have to learn first. And you've provided that opportunity for so many students, and in turn, like you said, their creativity furthers your research, furthers other research. Perhaps they go into something else, but your merging of those two goals has enabled them to do that. So that's very cool.
Yeah, I think also for example, the KEYS program, we had key students over the summer. They actually, this particular student that we mentored in KEYS is now, back in the group doing research with us as well. I think that's not a unique occurrence, right? That happens all the time. I think, opening students, studying can be quite dry, quite theory heavy sometimes, and it's easy to get lost in the coursework, right? And kind of also lose the reason why we do this in the first place. And if you have these hands-on projects that allow you to really experience, okay, it's important that I learn this Fourier transformation because I actually need it, that was always something that motivated me to get through the coursework in order to to be a better engineer in the end.
That's exciting.
Well, I want to, this has been a wonderful conversation. I want to end with one final question, something a little more lighthearted. So we like to think of our scientists as superheroes. So if you were a superhero, and we're not talking about a scientific superhero, if you were a regular superhero, what would your superpower be?
Yeah, that's a pretty tricky question. That is, I think, I really like to explore opportunities as they come along, and also leaving a little bit of room to kind of act in the moment and not have everything super planned out is sometimes actually quite helpful for creativity. So I think one of my superpowers is just to act quickly on opportunities that present themselves in the moment. And I think we talked about two examples where this was very much the reason why these particular projects came into existence very, very quickly as well. So I think that would probably be my superpower.
Well, I think your super sums it up very well, and I think those combine to really serve as a foundation for your work that really is going to change and save and help many lives and aspects of health and disease. So I want to thank you for that. Thank you for the work you do. Thank you for the mentorship you provide to our students, and thank you for joining us today. We really enjoyed talking to you, and hope to do so again soon. So, and thank you to our listeners for joining us for another episode of Science Talks. For more information, please visit our website at bio5.org. From all of us at the Bio5 Institute, we'll see you in the next episode.
Thanks to our listeners for tuning in to another episode of Science Talks. Continue the conversation with us next time as we learn more about the amazing science happening at the University of Arizona's Bio5 Institute.